Hello Calc students, welcome to your video lecture on continuity. We will begin with review of limits, then we will do some examples of continuity drawing on your pre-calculus knowledge. Finally, we will summarize and check for your understanding. Methods for evaluating limits. We plugged in when we had a continuous function. This is also an example where the function value at x equals c, at x equals 2, is the same as the limit value as x approaches 2. We could plug in because this is a continuous function. We can use the numerical method if we have a place where the function is behaving badly. In this case, the denominator is 0 if x equals 2. We could use a table of values and get closer and closer to 2 to see what's going on. In the case of this function, g of x, as x approaches 2, the limit value is not the same as the value of the function because the value of the function has been defined as 6/5. But if we were to do the algebra, factor the denominator, divide out the common factor from the numerator, we would get a different value. This is a removable discontinuity, and more specifically, a point discontinuity, which we'll discuss more in a moment. We could also use an algebra plug-in combination where we'd use algebra to simplify. This is a difference of cubes. Factor out the x minus 1 and then plug in 1. We have a hole at 1, and this is a removable discontinuity. So it's an example where the function of value at x equals c does not exist. However, the limit value as x goes to c does. A reminder, we went over this in the last lecture on limits. These are the limit laws. They're useful when you have more complicated limits to evaluate. They're also useful if you're looking at a graph. You can do it piece by piece. So use these when you are evaluating limits to make the problem simpler. So the key ideas for limits. The limit for the function exists at x equals c if and only if both one-sided limit, the left side of x equals c and the right side of x equals c, if both one-sided limits exist and are equal. In math notation, it looks like this. The limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. When those two are equal, then we can say that the limit as x approaches c of f of x exists. Some functions go to positive or negative infinity. Because infinity doesn't really exist, we say there's no finite limit at x equals c. If you say that the limit does not exist, we will correct you but not mark you wrong. And what do you recall about the squeeze theorem and limits? Did you like the tutorial? Okay, today we're going to talk about continuity, which takes the limits to a next step. This is also going to review some of the ideas from PCH, vertical asymptotes, horizontal asymptotes, removable discontinuities, or holes. So A and B are rational functions, C and D represent piecewise functions in the following examples. When I look at A of x, I see a rational function with a vertical asymptote at x equals 3. I notice that the degree of the denominator and the degree of the numerator are both the same. Therefore, the horizontal end behavior or asymptote is y equals 2 because I look at the ratio of the leading coefficients. So what does that look like? Ta-da! What it tells me is that I have a very big very big problem at x equals 3. That asymptote, vertical asymptote, is an infinite discontinuity, also known as an essential discontinuity. What that means is that there's nothing I can do algebraically to get rid of that discontinuity without changing the function completely. So anytime you have a vertical asymptote, you have an essential or infinite discontinuity. Equation B is another rational function. At first glance, I might think it's an asymptote at x equals 1, but if I look at it more carefully, I see that I can factor the numerator into x plus 1, x minus 1, divide out the numerator and the denominator, and I'm left with a line that has a hole at x equals 1 and the y value is 2. So hole at 1, 2. A hole is considered a removable discontinuity because I could simply redefine the function as this: x squared minus 1 over x minus 1 for x not equal to 1, and x equals 2, or I'm sorry, b of x equals 2 when x equals 1. I've essentially filled in the hole. So a removable discontinuity, or a hole, can be removed by redefining your function as a piecewise function. Function C is a piecewise function, but if you notice, this time at x equals 1, I've defined the y value to be 4 rather than 2, which means that I have a hole, and the hole is not filled in. So it looks like that, where the y value of the function is way up here, and I still have a hole. This is called a point discontinuity. A point discontinuity is in fact a removable discontinuity because I could simply rewrite the piecewise function as a correct function and give it the y value that it should have to fill in the hole. So it is a point discontinuity because we have a point that is where the hole, at the x value of where the hole should be, but not at the y value. So that is the third type of discontinuity. This function is a piecewise function, and there's not really a problem area except at the join point, so at x equals 0. What's going on there? So here we have a parabola, and here we have a line. And what's happening at x equals 0? Are they attached? We learned how to graph piecewise functions last year, and when I graph it, I see that in fact, no, they are not. If I'm traveling along the x-axis from -2 towards +2, I get to 0, and then I have to take a big jump to reattach the function. So this is called a jump discontinuity. This one is also not fixable. There's nothing you can do to the equation short of changing the variables or changing the equation to make it continuous. So this is known as a jump discontinuity. So you would most often see a jump discontinuity in a piecewise function where you have to jump from one piece to another. So, if we think about it intuitively, we know a function is continuous if I can draw it without having to pick my pencil up. We've just gone over 4 different kinds of continuity: an essential discontinuity, a removable discontinuity, a point discontinuity, which is a kind of removable discontinuity, and a jump discontinuity. In your own words, try to explain or describe what each kind of continuity is. In each of these cases, you should see how you have to pick your pencil up to draw the picture of the graph. So let's take a look at example 1. f of x equals sine 3x over x. In my head, I'm wondering, where is this discontinuous? And does the limit of f of x as x approaches 0 exist? Because I have a denominator, clearly the issue is at x equals 0, the denominator. We learned last week that we could plug it into our calculator and look at what's going on, and we should see that this is in fact approaching 3. So I could rewrite this as a piecewise function where the function is sine 3x over x for x not equal to 0. So sine 3x over x at x not equals 0 and 3 for x equals 0. So this is an example of a removable discontinuity. And if our calculators were actually a little more sophisticated, we would be able to see the whole at x equals 0. So this is the same function with a value given at the place of issue. So it's discontinuous at 0, and does the limit of f of x as x approaches 0 exist? Yes, it is still 3. This point is creating a value down here, and we need to have the value be up here to fill in the hole. So we could simply redefine it, so instead of it saying 0.5, we could say it's 3, making it a continuous function. So it is important to note that for both removable discontinuities and point discontinuities, the limit of the function exists. That is to say, the limit as x approaches 0 from the right of f of x equals 3 equals the limit as x approaches 0 from the left of f of x. Therefore, the limit as x approaches 0 of f of x exists and is equal to 3. Example 3 is a piecewise function, but in both of the pieces we don't have a problem area. That is to say, there's no denominator. So what are we going to worry about? We're going to worry about the join point, x equals 3, and our question is the value from the left equal to the value from the right? So where is this discontinuous? The question is it discontinuous at 3? How am I going to answer that? Well, I can do it graphically, that is to say graph it, or I can do it algebraically. I can graph it in my TI. This is a reminder of how we graph a piecewise function in our calculator, and we'll get this picture, and we can see that it is in fact not continuous at 3, and that's a closed hole, and that is an open hole. Algebraically, we could plug in 3 to the equation from the left. So from the left, 3 squared equals 9. And from the right, 3 plus 1 equals 4. So the y values are 9, oops, that's an equal sign, and 4, which are not the same. So the limit as x approaches 3 of the function does not exist because the limit as x approaches 3 from the left of the function does not equal the limit as x approaches 3 from the right. And that also tells us it is not continuous. And we remind ourselves that it is in fact a jump discontinuity. Example 4 is a question of a vertical asymptote. So we are expecting a discontinuity at x equals 2. And the question we want to ask ourselves is, does the limit of f of x as x approaches 2 exist? And we know that the answer, because we know that at x equals 2 we have a vertical asymptote, the answer is no, because this is an essential discontinuity. Example 5 is actually not an example, but a self-assessment. So you have 4 graphs, 292, 293, 294, 295, and using the Google form below, identify which kind of discontinuity is evidenced in each of these graphs. So thank you for watching, and tomorrow in class we're going to begin with a multiple choice quiz on limits, so continuity will not be on the quiz. Then we'll do some practice of the trig limits from yesterday's lecture in class, and then we'll do some practice on continuity on the material we just watched right now. Thanks.